Welcome to this NPTEL lecture on techniques and principles of modern radar systems. We have seen in the previous class the concept of delay resolution constant and Doppler resolution constant. We have evaluated that for a single rectangular pulse. Today, we will evaluate for it for a more realistic case of coherent train of carrier modulated pulses. So, now, this is a coherent train of, you see that high frequency signals, the envelope is a rectangular envelope and there is an on time, there is an off time, there is a high frequency signal. So, we can take that this is the time instant t is equal to 0 and this on time that we can say that this is our tau naught, let us say, because here there will be many confusing things actually, because the tau generally we call the delay, but this also when separately we tell this, that is why I am taking tau naught to be the on time of the envelope and the time period that I can say like this, that this time is the time period, let me call that capital T and that is nothing but this is PRI or the PRF, usual things for a pulse radar, and I am considering capital N number of pulses. So, generally we integrate n number of pulses in pulse radar. So, one time period is t, that is why capital N into t. This thing I am giving it a name t with a subscript of t. So, that means from here up to this or let us say that this is the nth number of pulse. So, I can say up to this. So, that means there are n number of pulses. So, we can it is not. So, there are, let me write that there are n pulses. So, that is why this is n t. Now, let us go to the expression. So, what is the transmitted pulse that I can write as cos 2 pi f c t, then n is equal to minus infinity to infinity rectangular t minus n t by tau naught, and so if this is the case, we can say the complex envelope x t can be written as, this will be e to the power, if you make, then it will come out that the carrier part will go T by capital N T. This is as it is. So, we know this is the, we can take the Fourier transform, the x tilde f, that this is a rectangular function. So, we know separately if we take this T T tau naught by T, we know that rectangular function means that will be a sinc function. If you do, it will come out like this. Then these two, so by the property of the Fourier transform, this will be a convolution relation. Sinc in FR tau naught into, for every rectangular thing there will be a delta function coming. So, this is the spectrum. You see that a sinc function convolved with a delta function, which is again whose envelope is given by a sinc function. So, total energy for this signal we can easily calculate. Actually, you see this is the beauty that we can find this, that what is the, because instead of finding the thing here, we can find the total energy, that will be minus infinity to infinity. This if we do, it will come simply as this. Also, to find the delay resolution constant, we need to find the fourth order term. So, if we do that, it will be approximately, it will come as 4 by 3 T T by T whole cube 2/3 . So, we can find the delay resolution constant to be this divided by this square. So, that will be 4 by 3 T T by T whole cube 2/3 tau naught whole cube divided by T T tau naught by T whole square. So, that becomes the resolution constants become 8 by 9 T T tau naught by dt. This is an important relation. So, I can give it a number 60, and so it shows that delay resolution constant of the finite pulse train that increases as the length of the train. Length of the train means t subscript t, that means the total duration. If that increases, that means if I integrate more number of pulses, the resolution get poorer. Now, when T t becomes t, when T t is equal to t, basically this is a single A case. So, that time you see this becomes 8/9, but if you see here that time this 4/3 also won't come. So, it is becoming 2/3 correctly. This 4/3 is coming because of the whole n number of those things, the delta functions, the rectangular functions, convolution, that part won't come. Now, similarly, we can find the Doppler resolution. For that, we need to find these terms x t square dt. So, this was simply the signal energy. So, from Fourier domain by Parseval oscillation, we can get it because already this has been calculated earlier. And one more thing we want, that this thing will be so the Doppler resolution in this case becomes so this again I can give a number. So, this will be 61, and so now I can take this product, that what is the delay resolution constant and the Doppler resolution constant product, that will be, if you do, it will be 8/9. So, this is simply 62. So, you see that in case of single rectangular pulse it is 2/3, in case of this chain of pulses it is 8/9. So, that means, since this is the product is fixed number. So, if I want to improve this resolution, that means, if I want to decrease this value will increase. That means, what I achieve in the range domain, the same thing in the same proportion I will have to forego in the velocity domain. So, this is the problem for this signal. So, that means, no flexibility in the design of the signal. So, also we will see another aspect of this product. So, let us again go to the match filter and consider that the case, suppose I have a match filter and let the bandwidth of this match filter is B. So, the input noise power Ni, so I can say that input noise power Ni will be 2B, if I assume the white noise, double sided white noise. So, it will be eta naught by 2, and if the signal is having energy x and suppose the signal is having energy Ex and the pulse duration of that tau resolution, then I can say the average signal power is SI, and that SI will be Ex by so what is the SNR at the input? That means I can say that SNRI. So, SNRI will be SI by Ni. So, that will be Ex by eta naught B okay. Or also let me call that what is coming out, that SNR output. Now, if for a match filter we know that if the input signal has an energy Ex and if it is sampled at the proper delay time T0, then SNR out, that becomes, we know Ex by eta naught by 2. This we have already seen. So, now what I will do, I will make what is the SNR gain sort of thing, SNR out by SNR in of the match filter, provided I sample it at a proper time at t is equal to T naught. So, this ratio, the output SNR out we know 2 Ex by eta naught, and SNR in this expression Ex by eta naught B tau resolution. So, this turns out to be 2 B tau resolution. Now, the input signal, you see that we know the if we take it the signal Doppler's frequency constant, if it is omega resolution. So, we can say that signal, the input signal bandwidth, we can take it as omega resolution. Then the match filter bin bandwidth should be, to avoid distortion, it should be greater than that or at least equal to that. So, this dictates that B we can take as gamma resolution. This is the minimum bandwidth, we will definitely make that because otherwise more noise will come. So, if we take this, then this ratio becomes SNR O by SNR I, this becomes 2 okay. So, what is this? This thing can be called as the match filter SNR gain. That means, the maximum gain you can get in terms of SNR from this. So, you see that for a this is an important thing, obviously here we will try to maximize it, and we have seen that for a rectangular pulse, single rectangular pulse, or I will write single rectangular pulse, then this gain will be, so before that, so 2 into 2/3, so that will be 4 by 3. So, you see that this product gamma resolution into tau resolution, that has an implication that that gives the SNR gain. So, how much SNR gain I can get maximum from the, if I use a single rectangular pulse, 4 by 3 for pulse train, rectangular pulse train, this gain will be 2 into 8 by 9, that is 16 by 9. So, this is 1.33, this is almost 1.8 something, but these are fixed. So, the point is this product, this gamma resolution into omega resolution into tau resolution, this is an important parameter. It gives good detection, this product if we can make more. Also we have seen that if we can minimize this, then the resolution improves, and also we should be able to do that independently. That independently we should be able to make this omega resolution smaller, and that should not affect the tau resolution. Tau resolution we should be able to handle independently this, but that is not possible in these scenarios, if we use these rectangular pulses or pulse trains etcetera. So, can we do something that we will now see? Actually, that is an important thing, that concept, the concept will go later, but we see a particular class of signal called linear frequency modulated signal. LFM signal. It is a simple signal. Now, suppose the signal at 0 time, its frequency is f naught, then with a constant slope the frequency is increased. Let us increase to this extent, that means f naught plus b by 2, and in minus time, that means from here it is decreased in the same slope up to f naught minus b by 2, or I can say that from this time from f naught minus b by 2 to f naught plus b by 2 it changes. That means, the bandwidth of the signal is b in a time tau naught. So, that means, if the frequency is swept linearly across the pulse width, and if it goes in the up, that means, the frequency goes up as the time advances, that is called up LFM, or sometimes it called up chirp. Chirp is the bird sound, very musical sound. So, if you see, if this signal is given to a loudspeaker, it will give you a chirped birds chirping. So, this is the up chirping. Similarly, you can have a down chirp signal, that means, this is your frequency, this is your time, and again so this is your B and this is your tau naught. So, this is your down chirp. Again, this will be your f naught, I think, yes, all the parameters. So, up chirp and down chirp. So, if we, you see, this is something like our FM signal, but not exactly that. So, if I see this signal in time domain, if it is x t, then with t the up chirp signal will be something like this. That means, frequency is increasing with time, and so I will say this is my up chirp signal, and if I have a down chirp, so I think so this is a down chirp signal. So, continuously in a particular fashion you can change it, but this is we will see in the next class the behavior of this signal as a transmitted signal. So, this is not exactly the FM signal that we see in communication. Why we will explain that, and we will see that what is its effect on the detection or resolution of the radar concepts. So, that we will see in the next class. Thank you.